on 19 August 2024 I was working on this circuit and I told that it was a properly working square wave oscillator, and I was very interested in that circuit. But anyway, I want to give the link in the description. This is, by the way, the constant current source, but now I went further with that circuit and did a few adaptations, and I have some hesitations about publishing this circuit because the waveforms are sometimes somewhat difficult to set. Anyway, I made a few important adaptations here. Let's look at the circuit first a little bit here. And here you see, say, the buffer stage, etc, etc. Anyway, I'm going to tell more about that. Here is that original schematic, and now I left this part here, this part completely. So now we have only this. So in this circuit we only have this part of that 1968 multivibrator, and it's now connected to 18 volts here. Takes a little current, etc, etc. Important to tell that when you want to make this circuit both in its original way, thus this, and it's now in another way, you need of course here a, say, kind of buffer stage, because when you load the multivibrator with some resistance, the waveform will change, many other strange things are going to happen, etc, etc. So what did I change in this circuit? I've used here not a fixed value resistor, but a potentiometer from 4K7, and of course, always important, a protective resistor of 1 kilo ohm here and here. And I've used here two resistors of 470 ohms. And that means that you can change the waveform in an enormous way. That's logical when you know a little bit about how multivibrators work. All these, this and this and this and this, and the capacitors are time-dependent electronic components, at least in this circuit. They decide, say, together the time, and that means that the waveform changes and the frequency changes, because frequency has everything to do with time. Let me show it a little bit. We are now on 56 kilohertz. This is a waveform, and now I'm gonna, say, change these four potentiometers. That are these, now these four potentiometers. Let's show what happens. So I'm going to turn this one. Let's see. So here we see some change. The other one, some frequency change. And here a direct frequency change. And of course, that original schematic of the 1960s was made in such a way that the oscillator could not switch off. But of course, when you use here potentiometers, the oscillator will stop when, say, the oscillating conditions set by all these different components, and then I mean especially the resistors, now the variable resistors are changed. That means that you need an indicator that is the circuit oscillates, and I've made it here with the blue LED. So when I turn the the knobs, on some moments the oscillation will stop. Let me show it. So here it stops, and now the blue LED is off. And here it is, the oscillation is there again, etc., and the blue LED is on. So anyway, of course this is, say, pure experimental, only when you want to do these experiments, and on Ali or wherever you can buy, say, a square wave oscillator that oscillates from 50 Hz up to 500 kilohertz or so. Could be okay. In this case it's experimental, and in my opinion could be more useful. Anyway, so what's important? This is the multivibrator now. It's here. And now the output is connected to this circuit, and that is the grounded base stage. So let me show it. Here is that first schematic. This signal goes here into the grounded base, and then into the driver of the blue LED, and to the grounded emitter stage that also amplifies. So here's the complete circuit. Could be useful when you have, say, a generator with a say problematic output, and then I mean that the waveform changes or whatever strange things that happen to the waveform when you take out the signal of that multivibrator or another oscillator. This could help. And these are these two stages. This transistor here is the driver for the blue LED. Here, not visible, is the grounded base transistor, and here is the end transistor, and that's a grounded emitter stage, and here is the bias for the blue LED. So that was that. Now about the waveforms. Well, they are not ideal, but perhaps useful. The first thing to say is that the complete schematic doesn't go so low, and then I mean below 400 Hz we have very strange waveforms, no square waves. Let me show it. We have this waveform on 941 Hz, and we can get lower, of course, by changing the frequency dependent potentiometers. I will try to do that to get to the lowest frequency here. Well, that's not very successful at the moment. Well, here now we are on 455, 449 for 30 kilohertz. This is, say, the waveform on the lowest frequencies. Kilohertz, did I say that? No, it's hertz. Anyway, say this is 400 Hz. This is the waveform. Anyway, now we go to the highest frequencies, otherwise the video gets far too long. Also interesting, of course, you can see that the amplitude changes, but anyway. So now we are on 1.7 megahertz. And this is the waveform. And you can change it a little bit, adapt it, make it more pure here with the bias potentiometer, and that is the amplification potentiometer. So in fact you have a too complicated circuit, but could be useful to make all kinds of waveforms. and these are the say the outer stages, the final stages. And here we have, only here we have the driver for the blue LED. It gets its signal from the output via 10 nanofarad capacitor. The working point, the bias here, is set with the 1 mega ohm potentiometer, and that blue LED lights up when the thing oscillates. So I think it could be interesting. It could be an interesting schematic to make this. When you don't have the time and the components, perhaps it's a good idea to buy a function generator. Anyway, this is hobby, this is experimental, and in my opinion the most interesting thing to do. But anyway, so again, let's look at the effect of the this is the amplification, this is the bias. Effect of the bias on that 1.7 megahertz waveform. It changes its frequency somewhat. It stays a quite good triangle wave. And of course you can change a triangle wave into a sine wave with the help of a filter, small capacitor, etc, etc. All experimental. Now I go to the lower bands, 715 kilohertz. I switch back to another lower band, still triangle by the way, 246 kilohertz. You can say now change it a little bit here. This is done by the bias. Change it a little bit into kind of square wave. Turning the bias again. So here. So and now we more or less 105 kilohertz. Now we get to the range where the circuit starts to work as a square wave oscillator. Change the bias again. You see all the effects, and here I'm changing the potentiometers that are in that multivibrator, the value. So anyway, you surely can see that it sometimes stops to oscillate. Not of course, but anyway. Want to try, we are now on 60 kilohertz, want to try to get the best waveform, purest waveform out. Anyway, so the only thing that I can say is do your own experiments. Thanks for watching. This is that output stage, and in the earlier parts of the video there is the schematic of that multivibrator. Still all experimental.